Yeah, stay tuned. There'll be some good talks next quarter as well. And today we've got a really interesting talk by Eduardo Cotilla-Sanchez. And so he got his PhD in 2012 from the University of Vermont, a beautiful state. He got his MS there as well. He must have really liked it. And he's one of the experts, a worldwide expert in power system resilience and protection. So he's done a lot of work, over the past 10, 15 years in that area. So he's one of these folks who's trying to keep the lights on, and when they go out, he actually understands why they go out. So why are there these cascading failures? And I've always enjoyed learning about his work because it's so computational. So he's really right on the frontier of modeling these hugely complex systems that are just enormously complex and continually getting more complex as time goes on with all the renewables. So I think he's going to be telling us a little bit about that complexity today, and I will just let him take over. So the floor is yours.
Thank you so much, Alan, for the nice introduction. And it's really nice to have such a good group of folks, linked to our School of EECS. I really like to talk about my work in general because I think I'm really at the intersection of all my background in electrical engineering, power system protection. That's the class that I teach this term, and I'm glad to see also some of our students that stay a little bit longer. So, I'm going to try to summarize some of the things that we're working on, and without going into a lot of the technical details. And hopefully we have a few minutes at the end so that we can chat about, whatever you like about this kind of work that we are doing here at Oregon State. So I want to talk about what are the modeling challenges so that we can discuss cyber and physical security of our electrical infrastructure. The largest machine ever created by humans is our power grids. And sometimes they fail in very dramatic ways and affect a lot of people. So I hope that throughout the talk, I give you a little bit of the sense of what's my approach in terms of energy equity and how we can collaborate to solve these problems, not to be in a CS silo or an ECE silo. And seen from outside of engineering, we are doing sometimes a little bit worse than some of the other fields in STEM. So I hope that we can keep this in mind as we are trying to do a more thoughtful integration of research with education. Sometimes we see in the news we're seeing a lot of talk about invest in green energy. What is happening with wind turbines? How is that affecting everything that happened in Texas with the storms and traditional fuels versus modern fuels and a lot of what we see in the news. I'm going to talk a little bit about Texas, but you probably heard a lot already, and we talk a lot about what are the things that went wrong. So hopefully I can make the connection that a lot of this is connected to kind of the area of power system analysis, economics, and energy markets. And you can see here that sometimes they are essentially, we divide the grid into for example areas that help us figure out what the markets are doing and how do we deal about the economics of it. And that's the connection that we did with what we see in terms of what is the access to energy, what is the energy access and justice issues. On my side of the research, I work a lot more into the area of power system reliability, resilience, and traditional protection. So when we do things like power system security, these are the area that we or the domain in which we solve our problems. And you can see that even in North America, the entities that regulate these problems are actually divided in a different way. That those footprints are a little bit different than what we're seeing at the top. So sometimes the markets, they do not overlap with the reliability councils and interconnections from NERC. So sometimes we see a lot of disconnection between the being sustainable and green energy so that we can keep the lights on in the face of energy access and justice issues and climate change, for example. But sometimes we don't really see this connection of how we can make things better also for the modeling and the collaboration. So I hope that I'm gonna spend most of the time here in this lower link that it's a little bit thinner so that we can think a little bit more about that part of our problems. I have a few examples that they are US centric, but I hope that some of the examples that I have from, for example, from Europe will also provide an international perspective. So this is the electricity consumption in the state of New York, population 19.5 million. It's essentially the same that all the electricity consumption in sub-Saharan Africa. This is from the IEA and how we can make the modern energy access universal. So this is a problem that I like to think about as I'm doing all the research with my graduate students and my undergrad students. Out of the 1 billion people currently without access to electricity, 84% are in remote communities. So I'll go back on my last example today to talk about energy access on remote communities. Before that, we can also look at domestic. So after COVID, if we look at some of the energy security in the United States, there was this survey that was done by the Indiana University, and it was a second round that was issued in September 2020. The first kind of like questions were asked in May 2020. And this is for a sample of the national population, 200% over the federal poverty level, the federal poverty line. So just kind of like excluding the top of affluent people and households. But out of this group, a national representative in this survey, and the margin of error seems to be around 2%, according to that study. They found that 20% of these respondents could not pay the bill, the electricity bill. 14.5%, they at least have received a disconnection notice, and 6.5% actually had disconnected. If we look at the disparities among our racial disparity among those households, you can see that 26.7% of Black and 27.4% of Hispanic respondents could not pay their energy bill. 19.2 or 26% have gotten disconnection notice, and 8.2 and 14.4 of Black versus Hispanic households went on to be disconnected. So we don't have to go very far to a remote location to see that there is an energy access issue. So technically, what I want to mention today is a few examples of how we combine things in terms of physical versus cybersecurity. My field of study is cascading failures. How do I tie security? Well, we like to run the grid in a way that we call N-1 secure. So we are very proud that in our electricity system, not a single failure should cause subsequent failures. So they should not propagate. Now, what happens if we have more, right? So if we have an N-2 contingency, so imagine that I get 2 transmission lines, or I have a storm, or I have some initiating failure where I lose not just one generator, maybe I lose 2 of them. Then we're potentially starting to get in trouble, right? Some of the studies, if we were having unlimited amount of budget, we could just protect and secure our system for N-K contingencies, right? How do we select K? It's very interesting. We could do a subset of that first contingency, and then we can do N-1 minus 1, which is not the same as N-2, right? We can have a given probability, but we could do a lot of things. We can do N-G, where the G are the generators, not just any particular element. So just starting in a simple way, something that we can see is how things are going to fail. Just starting, let's say, with N-2 contingencies. So imagine an event that caused a failure. Then that failure can cause another failure after that. So that's how things start to go wrong. We might have a protected device that removes a transmission line, but it actually makes things worse, right? So there could be different mechanisms of how that's propagating. But then we go to another failure that would not have happened if we didn't have the first failure to start with. And things start to propagate, and we get system disconnection, we get customer disconnected, and potentially loss of life. So in a few samples, there's some folks that study kind of like how those initial contingencies start, and a lot of our research is we assume that we have some initial contingency, and then we try to study those cyber or physical mechanisms by which they propagate. And we also try to limit, and if we can limit that propagation, then we will be essentially doing a good job. So, I'm sorry, I went back. So that's the few samples that I want to be mentioning is how can we do power system models that will help us not to study how these cascading failures propagate, but also how we can mitigate their reach. So this is the first example. Like I mentioned, we have very good examples domestic, but this is a good example that I like to mention. This, if you see here in the lower part of the text, is a European system separation. This cartoon, it is a little bit of the representation of the map of Europe, according to the report of this event, and this was November 4th, 2006. So what you can see in the map is for each country and each operator, you can see that in red is what we call the exchange program. And that was what it was forecast to have a transaction of power between different areas. And then in blue was actually the physical flow. When we run our power flow, this is what we had. So if you look, for example, on the left-hand side, Spain versus France, what transactions we had? Well, we were expected to have a 317 transaction, and then we only had actually a 263, right? Our France to the UK, that was pretty close. So what happened that day is that there was a cruise ship, so a big boat that was trying to go through a river in northern Germany. And a few months before November, I think it was September, they requested that they needed to disconnect a 380 kV line so that they could go under safely, right? Not getting too close to that transmission line. So it had to be de-energized. So they get close to November 4th, and then November 3rd, they say, hey, you know what? Actually, we need to go a little bit earlier. We arrive a little bit earlier. So can we move up the time that we are disconnecting by 3 hours on the same day? And then the utility company E.ON in Germany, they did really not resolve their model. Imagine that they couldn't recalculate this whole map, right? Because they didn't have that visibility at the moment. So they were just looking at the area in the top, the D for Deutschland, right? And see how I am not showing you the physical flows there because they could not see. They just had, the red. For example, if you see the Deutschland versus Netherlands, that 1950, that's what they were expecting. And between Germany and Poland, that was 500 power flow in that direction. So they said, we really don't have time to redo everything. So what we're gonna do is we also cannot share our forecast with the rest of the continent. So is it N-1 secure? Well, we hope so. And we're going to disconnect one line. Is N-1 secure? We should not have trouble. So my question mark was it N-1 secure? Spoiler alert, it wasn't. So if you see that arrow now between Deutschland, there was a lot of wind that was not well forecast, and the flow actually was much larger in that direction. And then between Germany and Poland, actually the flow that happened was in the other direction to what they had forecast. So this is a phenomenon called loop flows. Sometimes in the East Coast, we call them parallel flows. But we've done some work trying to minimize these flows in very large areas. So it was not N-1 secure because they thought that this bus switching in that location, without doing the whole simulation, they said, well, if we do this, then this current in this transmission line will increase by 80 amps, will decrease by 80 amps. It actually increased by 67 amps, so the transmission line tripped. After that, we had essentially a textbook example of cascading failures, and the whole continent essentially got disconnected and is separated into 3 different regions, at least for 38 minutes. So very dramatic example of cascading failure. You can see in this map on the upper right, we can see the 3 different regions. So the Southwest, kind of like Northeast, and the Balkans area. And then you can see the frequency. So you can see how at the beginning, the 3 frequencies were around 50 hertz. So the European grid is synchronized at 50 hertz. And then that event happened. And the 3 grids gets disconnected, and each one is at their particular frequency. So in green, we saw that because there was a lot of wind, they have extra generation, right? So they were trying to curtail. And the mustard color or light orange, depending on your monitor calibration, they had a deficit because they didn't have enough generation because they were getting a lot from Central Europe. So you can see how the frequency goes down because they cannot keep their demand going. So what you see on that big swing is over that period of time, they were low shedding, they were rolling outages, and they were dropping customers so that they could bring that yellow line back to somewhat nominal operation, closer back to 50 hertz. So over 16,000 megawatts of demand were lost. And then the blue area, they had a little bit of under demand, so they dropped some demand as well, but they were actually a little bit more balanced when they broke down into the island. So they were a little bit closer. So, and then those spikes that you see between the green and the yellow, for example, was a try to reconnect and resynchronize the grid. So imagine the wear and tear of those machines that they 9 times tried to resynchronize and have those wild oscillations of frequency. So over 38 minutes that we had the whole system dropping load, disconnecting customers, and everything split into 3 islands, losing over 16 gigawatts of demand loss of those customers. And then look at that tries of reconnection between the customers and the 2 areas, and those machines trying to reconnect in a very wild manner. So that was a very dramatic event from the technical aspect as well. So move forward to January 8th, 2021. We had a lot going on those couple of days in the US, unfortunately. So you might have missed that Europe actually had another system separation that day. And the consequences were not so rushed because only 233 megawatts of the end customer demand was lost. And then the other things that they were disconnected were actually contracted, low shedding, pre-planned contingency plans. So you can see in the frequency also, there was an excursion of frequency. The system broke into the 2 islands, but then it was almost steady state until they were figuring out that they could bring some generation online and disconnect those customers that essentially had an agreement on disconnection according to frequency. And then only 233 megawatts were actually unintended rolling blackouts, right? So it's a huge contrast of what happened a few years ago. So what happened? What do they improve in these few years until January, a couple of months ago, that they avoided a disaster of potentially losing a lot of lives and another event with a lot of cascading failures? Well, there was a lot of things that happened. But one of the things is that there was a recommendation after the previous event that was to create a European awareness system so that you could share all those flows like we were having in that cartoon map and have a better coordination between the transmission system operators in Europe to exchange that operational information in real time so that they could react quickly in case of unusual system condition. So that's for us and for our group, the motivation to do a lot of this research. How can we improve? How do we share the models and collaborate with those models so that we know the technical aspects of how to mitigate these events? A lot of similar readings are in our cascading failure working group. I'm serving as a vice chair of an IEEE group where we coordinate and discuss and research these events. And right now, our leadership board is a really good mix between PJM is the largest utility in the US with the largest independent market in the East Coast. And then we have also European representation and national lab representation, and over 200 members very involved in our activities. So if you go to the website, you can see some of the publications and the dissemination that we do on these topics. One work that we did very practical for this talk and this research is in 2018, we got together and say, well, what kind of tools, what kind of models are we using to compare things in terms of cascading? Can we essentially run like a horse race and compare what are the elements of failures that we're incorporating? What are the elements that we are missing? So we essentially compare a lot of models that we have out there. In the left, you see the name of the model, for example, the Manchester, OPA, practice, and the type of model. Some of them are research grade and some of them are commercial. And how do we consider those initiating events? In that slide that I have n-1, n-2, do we get a list of events? Do we do a probabilistic analysis? How do we select the other events that happen? How do we link those? How do we select the contingency list? And very importantly, and I'm very interested in this, what are the different cascading mechanisms that we consider? Is it line overload? Is it hidden failures? Do we tell a relay, this is for my students that they are citing protection, do we tell a relay to trip and then the relay gets stuck and they never open the circuit breaker? Can we incorporate all of that for a system level problem? So what we did was say, well, we tried to compare what are the things out there on how we compare the whole system. And we did just, it seems like a very simple graph, but there was a lot of simulations on the same system and trying to see if we agree. This is a survivor function. So on the horizontal axis, you have the amount of customers that you lost, the amount of demand that you lost, normalized to the peak load. So that 10 to the 0, that would be 1. That would be total blackout, everything disconnected. And then on the y-axis is the probability that we will have a demand loss larger than that number. So as we move to the right-hand side, that tail is giving us the chance that we will have a very large blackout. And then to the left, smaller blackouts. So you can see that we compare with some historical data from the West Coast. So that green is actually the blackout sizes for historical data here in the WEC, in the West Coast. And then how the different tools are either approaching how close we get to that simulation of cascading failures and the loss of all of those events with different tools. So you can see that there's some agreement with the chance of having a mid-sized blackout during the middle of the graph, but then on the tail, we kind of disagree a lot on what is the chance of having a very large blackout, like something like the event that happened in Europe. If we dig deeper, we can actually go and see, okay, imagine that I want to say, are the same lines the ones that they are involved in this blackout? So imagine that on this top of the table, we see, okay, where is the line 107 to 108 or 307 to 308? So that's like from the two endpoints. And then if you read vertically, we can see how different simulators give you different agreement of where were the troublemaker lines, right? So if you go, for example, on the first column, line 107 to 108, that shows us top 3 troublemaker only in 2 models, right? It doesn't even show up as a troublemaker in the other models. So there's not a lot of agreement. It seems like the best that we can do in this case, if you go toward the middle of the table, the line between 314 and 316, that shows as top 4, top 2, and top 1 in 4 different models. So it seems that that's a problematic line. You know, for example, the one that cruise ship was going under and disconnected, that was going to be a troublemaker. So we didn't have time to run all of this simulation. So how can we exchange and see what the time will be so that we have some agreement? It is a little bit tricky. We don't yet have a lot of agreement on this. So one of the efforts in my research group is that we're trying to do more open source simulators so that you can essentially try to reproduce your cascading paths and compare with what is the timing. So this is a link to our open source simulator. And it's not super fast. I mean, it's written in MATLAB, so you can play with it, but we are working on some more advanced version of it. But it can tell you, so in the left is a map of Poland. Poland has an open source grid, at least some planning cases. So they're very kind enough to release some of the data so that we can play with it. And we can cause those links of events. So you see those numbers. So that 0 are the n-2 contingency that was initially taken down. And then we can see how different events, those red squares are places where the load shedding will happen. And you can see that you can find red square all over the top left corner, right? And they were very far to those initial events. And then the important thing also is to have the timing of the blackouts, right? So in the lower panel, you can see a graph where as we move over time, right, 150 seconds, 200 seconds, and then you see the amount of outages that we have. You can see how at the beginning, those outages were somewhat slow. So we have like 100 seconds to intervene and do something between the first line and the second line that happens to fail, and then the third line. But then as we increase into that event, we can see that it's happened very fast. So you can think about human intervention time versus machine intervention time. If we're doing something like AI or machine learning, we need to be careful of what is the computational budget that we have according to that regime. So we find some agreement on slow cascading regimes at the beginning, and then kind of like faster cascading regimes. So with this simulator, we can, you can just check the things that you can play with and create your cascades. The project that we're having right now is related to cybersecurity. So I don't, this is work in progress. So I don't have a reference to share right now. But what we're trying to do is, for example, on the left, imagine that you have an attacker and you are, for example, using smart meters to oscillate loads on, off, and cause a particular frequency that would be very, very damaging for the system, right? So for example, the class A attack is choose a particular frequency. The attacker could know something about those forecasted flows, those red arrows that I show you in the European map cartoon, and then they can see where they want to attack and what kind of attack they want to produce. For example, connecting and disconnecting demand, or using two different frequencies. So in the right hand side, you can see kind of the response of our mitigation scheme. And I will not go into the details, but that's that one will be essentially the 60 hertz. That's the generator speed normalized. So similar to the 50 that we saw in the case of Europe. And then the frequency deviations that will occur if we have an attack of 25 seconds in the top panel versus 60 seconds in the lower panel. So you can see how the attack in the lower panel is actually more successful from the point of view of the attacker, because they were able to essentially shut down that other subgrid that was in orange, and it was never able to recover and go back to steady state. So essentially they got half of the country disconnected in that case. So those are the kind of things that you can do and play with different strategies if you have something that it's open source, because we can kind of like mix and match, for example, and get some of the things that we learned in machine learning strategies about how to attack and defend, right? Do some sort of adversarial attack. So that's one of the examples. The other example that we had with, this is also the Poland grid and using learning schemes. This was for the reconnection. So this belongs to, or it matches with that problem that we saw earlier in Europe, where they tried to reconnect like 9 times over a period of 38 minutes. And we didn't know if those sensors might have been compromised. So this is some work that we tried to say, okay, if we had a machine giving us some insight, essentially a computer simulating this, and looking, for example, whether it's a good idea to reconnect that blue portion of the grid, so that's Poland, that's like 1/5 of the Poland system. And when is it a good time, right? Do we need to wait 38 minutes of those machines going wildly? How many points do we need to look? So these locations on the left, those are those red points where can we make a decision by looking at how those boundaries are doing? And can we teach the computer to tell us whether it's a good time or not? So in the top row, you can see that compromised by a cybersecurity attack. So in that case, you want to have solid information, very timely, but also very close to where you're trying to do the reconnection. So just another example of things that you could do with such type of simulation. So I'm gonna have just 2 more examples that are also kind of like capturing and putting together all of these topics. The first one is some recent work that we did in collaboration with Idaho National Lab, and my former student Felicia Cicilio. She's the first author here. She just graduated from our school, and she's now a faculty member at University of Alaska Fairbanks. So we did this work in collaboration and trying to see what are the models telling us when we're trying to get our resilience threshold. So in this case, you can see this is a very typical trapezoidal curve of how we measure resilience. We have optimal operation, and then once we have an event, that line goes up because we are essentially having a disturbance in progress. And then we have phase 2. Those are those 38 minutes with that post-disturbance. We have some degraded state, and then we try to restore things. So can we start looking at what are those adaptive capacities so that we can say, this is how much wiggle room we have without going over that resilience threshold. In order to do that, we can also keep playing with what are good models to do this. So now I'm gonna talk a little bit about Texas. So we actually use one of the Texas synthetic grids so that we can share them. This is some of the work that Professor Tom Overby at Texas A&M has been doing with his group. And they have essentially synthesized several power systems that look very similar to the actual grid, but they are synthesized and they are not on the exact location so that you can do studies that do not compromise the security of the system while drawing interesting conclusions. So I think this is excellent work that they are doing so that they share this example. So what we did is, well, we want to look at the time domain simulation and put it into some of our models. So what our group did was to modify that Texas system that was synthetic, and then we added some of the elements that we consider that they are very interesting for cascading outages. So not just for planning, buying, and selling power. We got that power system and we added, for example, some of the dynamic parameters that you would use with wind generation. So you can use a similar study, for example, and be able to forecast what will happen if we have very cold weather in Texas. This was last year, so we were not working on that particular event because we were not forecasting that particular future of what happened in January. But we did a similar example, which was, what is a high impact event that could be simulating a hurricane passing through coastal Texas? So that was our initial conditions. And then we have, for example, different line outages. It was a 3-phase fault, and all of that happened over the course of 10 seconds. So that was the scenario that we were modeling. And we also wanted to contribute back to people being able to run that analysis. So we shared that as open access, that data set. You can see that screenshot from Zenodo, and be able to, for other groups to share that model without having to give all of the details, right? So this is kind of like the details of the models, what's going on. This is not something that it's easy to disseminate, right? So we try to abstract all of those details. The protection models are also very tricky. This is a homework from my students. that we were discussing in class 2 weeks ago, right? Very black and white, very kind of like old school. It kind of reminds me of this picture in our building from our power system group graduating from OSU in 1971. Very small group. So we can now get into all of these models and details that in order to disseminate these results. What we can do for that Texas case was, okay, let's look at different scenarios where we have distributed energy resources, and then we say, okay, according to the penetration of those resources that we have, either fixed or with different probabilities, how well can we do for the degradation of the system and the recovery? And then we can share them, and then we can say, well, dynamic responses on the left are those like total load scenarios. And then on the right-hand side, we can do a probabilistic analysis where that green dotted line will be the resilience threshold, right? So we can start trying to think like we did at the beginning. Can we compare those models? Do we have time to do the steady state, or do we have time to put all the details of the wind turbines and things like that? And then, of course, this is difficult to speak in such a short time without all of the details. So the example that I like to give of how I talk about this paper is how I probably summarize it on my Twitter feed. So I said, we just published this. We need to be careful. We saw a 15% difference between some of the dynamic and static models. We can get voltage support. It works pretty well. It gives us a 4% of advantage in those models. And we need to be careful with seasonality, for example, with wind. And then you can put some GIFs so that people remember what you're talking about and capture them into that example. So that's example number one. And then the example number two, I'm gonna use this my last 5 minutes for my second example. I'm gonna connect to my energy access topic that I mentioned at the beginning. And how can we improve that energy access for remote locations, right? When we are not so well interconnected to a large system. So microgrids are a way in which we can organize energy infrastructure to deliver electricity, either in coordination with the regional bulk power system or autonomously. We should be able to switch back and forth by their own definition of microgrid. If you look at the United Nations Development Program, they estimate that in their Energy for All program for 2030, they recommend that 50% of the required investments, they need to focus on things like microgrid infrastructure so that we can essentially keep this goal of providing energy for all. So one of the work that we did, this is also with my former PhD student, Felicia, and our collaborators at One Power Africa and Northeastern University. So we were trying to put together a tool that will be also open source so that we can do design and planning studies for rural electrification. So a lot of the work that they had done with One Power, and particularly in Lesotho, very close to South Africa, they were essentially having a way to put generation. So we have generation and we can do a good analysis. We have load profile, we can sizing and parameters. So that was a part of the software called essentially UGrid with a PSO, a particle swarm optimization algorithm. And then at some point we get, okay, this is how much it's gonna cost us to do this. And then on the right-hand side, we need to put the infrastructure, right? How do we put, for example, the microgrid? How do we put the pole placements? How do we do the network layout so that we can have a resilient system? So in this example that we show in the paper, it was a village in Ha Makebe, which is one of the villages that you will find in Lesotho. And it has 212 houses. They have the peak load. They were doing a battery size, solar, they have a plant generator, and that's the levelized cost of electricity that we got from the optimization problem. So the next thing that we did is, okay, let's try to actually draw the microgrid. So in our toolbox, what we did was essentially we can go to that village map and you can essentially draw what are those exclusion zones, places that you cannot have those poles, right? To try to make it very resilient without getting in trouble with putting infrastructure very close to your customers. So we did this manually in this version of the software, but this would be something that it would be really great for combining with a machine learning AI application where we can look at better design of that microgrid. And then the house locations will be on the right-hand side. So what we did with that was to put it into our algorithm and provide different microgrid solutions. So here in the left, we essentially have the 0% extra that we put to improve resilience. So that will be kind of like the cheaper version, right? And then as we move to the right-hand side, we obtain from the algorithm more advanced solutions that they're going to be more resilient and more reliable, depending on how much budget we have, right? So one thing that will pop in your screen is that as we move, for example, from 10% to 25%, that loop in green, depending, the color tells you the different voltages, the loop in green is essentially closed, so things are more redundant, right? And then to the right-hand side, the 100%, see how it closes a couple more loops. Even the red loop on the left is also make more redundant, so therefore it's more resilient. So so the algorithm, we can essentially tune that resilience depending on how we want to set up our microgrid according to all of those constraints, even considering our customer locations where we can essentially not going to be able to put a pole, right? And all of those inside the algorithm, those 4 scenarios, of course, will have an additional cost of putting that extra infrastructure with respect to the baseline solution. So that was a second example that I wanted to show, and I'm at the end of my 45 minutes. So just to finish up, this is some of the previous editions of my power system classes and protection and power system analysis. This is right pre-COVID. So what we will do around campus is to go with our students and show them the infrastructure and have a kind of like a bike to the field day. So hopefully we can go back to doing that very soon. And I think that's all that I'm going to have for today. So I'm super happy to ask, to discuss any questions that you might want to ask. And this is, of course, my email, website, and Twitter if you want to have any follow-up question for later. Thank you very much.
Yeah, thanks, Eduardo. So we've got time for questions. So you can either just unmute and ask, raise your hand, type it in chat. Any of those options is fine. So while people are thinking, I'll just start with one. So it's kind of interesting to think about the relative value of. So it seems like there's an information problem, right? So for these cascading outages and outages in general, there's an information problem. There's a modeling problem, and then there's a decision-making problem.
Yes.
Right? And I'm just curious to get your perspective on the relative value of each of those, like improving each of those in the next 5 years, and what you think is most important.
Yeah, that's a great question, Alan. I think we need the 3 of them, right? But in my case, I work a lot in the modeling portion, and I think it's very important because if not, we're essentially doing investments on places that they are not the right place. So of course I don't have the full picture. So I think we can improve things like the modeling, and something that my research group is working on. But I really think that like I was showing at the beginning here, I hope that you can still see my slides even in small mode. I guess the idea that I'm coming from is like, even though those 3 aspects might seem separate, and I'm drawing the map here with different areas, the grid at the end of the day is the same one, right? So I think if we have better models, it's going to help in those 3 tenets. So it's a good question. I don't think that I have a great answer beyond it depends.
I mean, I guess another way of thinking about that is, what fraction of the major outages could have been prevented with just better information and humans processing that information?
Yeah, I think a lot. If you look, I think if you look at the example that I gave for Europe, the situation awareness and the exchange of information, I think that was the number 1 indicator on how that reaction and the response was improved with respect to the 2006 blackout. So I think it's very important to have that real-time exchange of information, but that could not be possible if you didn't have a model that was fast enough to do that in real time. If you were doing every possible contingency of n minus k, you would not be able to do that in the 3 hours of leeway that the ship was giving you before people went home for the night and they had an estimate of the flow for the next day. So yeah, I think it's a great indicator of your return on that investment. I think, the example of Europe, that situation awareness was, I think it was one of the keys. But it's also based on what do you have on the back end on that engine.
Thanks. Yeah, do we have some other questions? So Vishvav has a question in chat. Do you want to just unmute and go ahead and ask it?
Hi. Yes. Hello. Hi, Dr. ACS.
Hey,
can you hear me?
Yes.
Yes. This was a really great presentation. I have also been, for the larger audience, I have been Dr. ECS's student for the power systems analysis course that he teaches. So I could relate to those substation visits. But yeah, so my question was, that you presented, how we can rank, some assets and their criticality.
Yes.
And so can you talk a little bit more about how these criticality of assets get used in designing of the corrective actions or remedial action schemes, which are yeah, and also the second part of the question is in case of modeling resilience events, like the high impact, low probability events, should we really be considering, criticality of a combination of assets, which would lead to higher impact? And if so, how do we find the criticality of a combination of assets, right? I think that is one of the problems I have faced multiple times.
There's a lot of work out there. Vishwa, you have a really good question. Just to make it very brief here, this is the question of, do we need to do n-2 or do we need to go to n-k where things are very large, right? There's a lot of research out there, and some of the folks are doing things like, for example, looking for combinations that they are malignant, and we are learning even from cancer research, looking for biomarkers that when they give you combination, those are really bad initiating events. From this point, which is kind of like an empirical simulation with different outages, right? What we are doing is, and maybe the cursor was not given before, but in this case, we're trying to find agreement, right? So in this case, this line here was showing up as a top contender. So if I were gonna do, for example, I don't have time to do n-3. If I was gonna do an n-2, I will get some of the top lines that show up here to do a more detailed analysis, right? So you could do it kind of like in 2 stages. First, you kind of like get what are the n-2, n-1, -1. And then in order to see the interaction and the combination, then you will have to go to something more detailed, like the time domain simulation, and use those as critical initial events for your scenario and risk-based analysis. Does that make sense, Vishwa? So it is a complicated problem, but the initiating point is to find agreement on what elements are either involved in the initiating event, or the lower panel is those lines that show up as like being in the middle when those cascades happen, right? That propagation. So you can look at those in 2 different ways.
Yeah, that was great. Thank you so much.
Yeah, thanks, Vishwas.
So Ethan, you've got a question in chat. Do you want to just unmute and ask it? If Ethan's there, or Eduardo, you can
yeah, I just read that. Yeah,
okay.
Thanks, Ethan, for that question. Ethan was asking whether we could do something like scarcity pricing to essentially, when we have an emergency, to be able to do something that kind of like overrides the market. I'm not a power system economics expert. I'm kind of more on the physical and cybersecurity side. And so sometimes the pricing and those initiating factors, I have a kind of like external boundary conditions for me. So my group hasn't been looking at a lot of pricing, but I think you have a really good point. My opinion is that we need to look at something like pricing, like scarcity pricing, or some way of having an exemption to those rules of the market when we have an emergency, because we cannot do something like charge customers $16 billion when we have a cascading outage. So that's my opinion, that we need to have a way to put the market as well in emergency mode, the same that we do emergency operation from the protection side. But yeah, my research is not really in the market, but I can see how, of course, it affects a lot of what's happening in that time period, right? That I was showing, for example, here, right? That time after the event that we need to intervene very, very fast. If those generators are essentially operating under market rules that they think that they are the same that the previous rules up to the initiating event, then it becomes very tricky, right? And we have kind of like a back and forth and fighting. So super important. I would love to do a collaboration where we can incorporate some of those rules into that real-time planning. Yeah, thanks for that question. Hopefully that more or less addresses the concern, the ideas that you were raising. Really great point.
Okay, are there any other questions? Yeah, I guess I just have one more. And so, yeah, we hear a lot about sort of green energy and, trying to be more sustainable. And you're about reliability and resilience. And so how do you think about the trade-offs between these two things? Are we just going to have to get used to the lights going off more often if we want to be more sustainable?
Not necessarily. I think one of the takeaways that we have as we are integrating, for example, these scenarios that I had down here on distributed energy resources, which could be a combination of, for example, batteries or wind energy, solar PV, which is going to keep growing. I think, and I have a separate work on one of my students was looking at this problem, is that how many times do we get into that state of being critical, right? So sometimes the trade-off is like, we just need to be a little bit more careful, but the outcome is like, we were not losing any more customers or any more load throughout the whole year. So in our model, kind of like things are going well, watch out. And now we are in emergency mode when we are increasing those renewable sources in the work that we did. And this is for, of course, we were using this for wave energy, and it's a very particular case. We could do this for larger studies, but with our wave energy models that we were integrating this into the West Coast, we never got an increase that was on the emergency mode. We saw some in and out of, hey, watch out, we need to be careful with what are the capacity resources. So I think if we are careful and we make those distributed energy resources more flexible, we can definitely do it without losing more customers or making those events worse.
Okay.